I'm going to talk about how to include pre-existing turbulence in the upstream in fully kinetic simulations of shocks. So let's start with a very general picture. So to interpret the non-thermal cosmic messengers such as cosmic rays, radiative and neutrino spectra, we need to do several things, but the first thing is to understand the acceleration, particle acceleration mechanism. Of course, one of the most well-known acceleration mechanism is shock acceleration. So just a short recap of what a shock is. So if we work in a frame where the shock is at rest, so we have a shock front here. This is just a sharp transition between supersonic and subsonic flow. So we have different flow velocity in the upstream. So this is undisturbed medium, and in the downstream, which is disturbed medium. And now, if we include magnetic field fluctuations on both sides of the shock, so that the relativistic particle can be scattered back and forth multiple times, this leads to growth of energy, which is a well-known diffusive shock acceleration process. And now, if we consider distribution of particles and strong shocks, we get the universal power law. But as you can see, there are two main requirements. So first requirement is that a particle must freely cross the shock front, which we can write this as a condition that the particle gyro radius must be larger than the shock thickness. And of course, this is much stronger constraint for electrons than ions, which is known as electron injection problem. Another important assumption is that we need to have these magnetic field fluctuations. So what's the origin of these magnetic field fluctuations? So they can be pre-existing, so pre-existing in the upstream, and then they are transmitted through the shock to the downstream, or they can be generated by the energetic particles themselves. So already we can see that the shock acceleration is a nonlinear and multi-scale problem, and there are three main agents that play. So we have thermal particles, we have non-thermal particles, we can call them cosmic rays, and then we have plasma waves and all these interactions between these three components. So it's very hard to study these nonlinear processes all at once. So what we can do, we can divide it into chunks and focus on some aspects. And in this talk, I'm going to focus on the influence of large-scale turbulence on thermal plasma and especially on electron injection. Okay, so to study electron scale processes in plasma, we need to use fully kinetic simulation. So this is just a short recap. So we follow samples of phase space as single particles, and we call them computational particles. So instead of solving the Vlasov equation, we solve the Vlasov equation, but by following trajectories of these computational particles. And then we can probe all the nonlinear phenomena in collisionless systems. But the issue is, as it was highlighted in the previous talks, scales. So this applies to all the systems except this spider pulsar. Okay, so for example, if you consider a supernova remnant and shock acceleration in supernova remnant, and so we need to resolve characteristic frequencies, so plasma frequency. So what we can do, and this is for estimate for 2D simulations, let's say we end up with simulating around 10 seconds, but in reality we have 11 orders of magnitude longer evolution. Same with spatial scales. So now we need to resolve electron scales like electron skin depth, and again, 11 orders of magnitude. So global peak simulations of shock acceleration in astrophysical systems are not quite possible, but maybe there is a way to improve them and improve effects that are on larger scales that we can resolve with peak. Okay, so our first attempt to this was to include pre-existing turbulence in the upstream, and that is driven, for example, on ISM scales, and this cascades down to kinetic scales. Yeah, so motivation, observational motivation is that we have this radio and X-ray non-thermal emission from supernova remnants. There is also gamma ray emission, but it's hard to distinguish, of course, between leptonic and hadronic origins. So we have observational confirmation that electrons are accelerated by shocks in supernova remnants. But there is this electron injection problem. So what happens if you have pre-existing turbulence? We may modify particle dynamics, plasma instabilities, and then acceleration conditions. Okay, so first step is to generate turbulence. So this is very simple. We do this in a periodic box simulation. We just steer plasma, so impose initial velocity fluctuations and let it evolve. So this is compressive. We get compressive decaying turbulence. And since we are in the dissipation regime, most of the energy goes to particle heating, which also limits the amplitudes of the turbulence we can have. So stronger the turbulence, the more efficient is the heating. So the higher the temperatures and lower the sonic Mach number of the shock. And we want to keep the shock Mach number high, as in supernova remnants. Okay, we do 2D simulations. So we have fresh plasma injected here that is reflected over conducting wall. This reflection creates a shock that propagates to the right. So the simulation frame is equivalent to the downstream rest frame. So we need to keep adding fresh particles in the upstream. Now, if we add slabs of turbulent plasma prefabricated in periodic box simulations, we can see that at the interface we have sharp transition, and we want to smooth this out. Otherwise, we get some strong gradients in Maxwell equations leads to numerical transients. So we pick up a transition zone when we are going to smooth this out. So we do this cell by cell. So we have cell from one slab and cell from another slab, and we have different particles at different locations with different velocities and then different values of electromagnetic fields. So first step is to interpolate electromagnetic fields. This is pretty easy. Then we interpolate the velocity distribution function. So we need to calculate. We don't have explicit velocity distribution function, so we calculate moments of the distribution and then interpolate the moments, delete all the particles and regenerate them using this interpolated distribution. Then we need to do some corrections. We don't want to have non-zero divergence of the magnetic field, and also we have additional charge noise, so we do correction for the electric field and divergence B cleaning, and then we can evolve it. Okay, 3 minutes left. So we started with perpendicular shocks. We do not see that much different if we include density fluctuations of order of 10%. So let's move to oblique shocks. So this is homogeneous shock. At oblique shock, we have a population of electrons that can outrun the shock. They propagate towards upstream where they drive instabilities, for example, oblique Whistler instability. And closer to the shock front, these oblique Whistlers create these nonlinear structures, so we can see this as density cavities. And now if we add pre-existing density fluctuations, we can observe much larger structures that are going to strongly influence the particle dynamics close to the shock front and then acceleration conditions. Okay, we can see what happens with the Whistler instability. So Whistler should be right-hand polarized, so we can calculate polarization of the waves in the upstream. So let's focus first on the blue line. So in the far upstream, for the homogeneous case, we do not have signal, and then at some point we have exponential growth, which reflects the growth of the Whistler instability. Same for turbulent case, but we have larger amplitudes, which means that the evolution of the instability is affected by the pre-existing turbulence. okay, now how does it look in the time? Actually, so I'm showing this for homogeneous case, the image is clear, but for the turbulent case, it's similar. So in time, the region where the instability is driven expands, but at the same time, the growth rate decreases, so that close to the shock front, we get similar values of the magnetic field amplitudes. Then also, electron distribution is affected, so we have a much wider distribution of these shock-elected electrons. They do not propagate that far. Okay, so this is probably going. So yeah, and then we observe more efficient electron acceleration in the case of the turbulence. So I do not have much time, but another step is to get even stronger magnetic field fluctuations that are driven by streaming cosmic rays. So streaming cosmic rays are going to generate, for example, non-resonant instability. So we can simulate this Bell instability in periodic box simulations. We can see growth of the nonlinear structures at the saturation of this instability, and the idea is to include this in a shock simulation. Why do you think that it may affect? Because also, like during the evolution of the instability, we have pretty strong particle heating, so it might affect particle injection efficiency. We start with higher temperatures, but at the same time, maybe larger the temperature, then lower the Mach number of a shock. So this is my summary. We presented a method that includes effects, a way to include effects on larger scales than can be resolved by peak simulations. So this pre-existing turbulence affects dynamics and shock microphysics for non-relativistic high Mach number shocks that have oblique angles. There are still many open questions. For example, like what is the turbulence level at kinetic scales, and how it's connected to particle heating. Maybe if we have turbulent structures on larger scales and shock transition, we get shock corrugations. Yeah, and the thing we are working on right now is how streaming instabilities affect particle injection and electron heating. Okay, thank you.
Are there questions? Yes, Lorenzo?
Not sure. That's a obviously good question. But so in the spectra that you showed for the comparison of the homogeneous case versus the turbulent case, it looks like the normalization is not really changing. Like I would say the injection fraction is not really changing, but maybe what's changing is the acceleration rate. I was wondering whether you have a way to say whether the turbulence is changing the injection efficiency or whether it's just providing a faster scattering rate.
Yeah, I think this is a good question. So we are currently investigating the reason why we observe this spectra. So looking at particle tracing, what happens in details. So whether like you're saying, it's more about scattering, or basically whether we observe similar mechanisms that accelerate these particles. Yeah.
What was the inclination here?
So this is 60 degrees out of plane.
Out of plane.
Out of plane, yeah.
Because in plane it wouldn't be accelerating anything, right?
So in plane, I think if we consider in plane configuration, then the Whistler instability is suppressed, and we do not see this oblique whistler, so that, yeah, maybe...
And electron acceleration is suppressed.
Yeah,
yeah. Just very quickly, so you said that you want to have turbulence on scales larger than what the shock makes by itself, but I think what you've shown is kind of the scales comparable to what the shock makes by itself. Or did I get it wrong?
Yeah. So here, turbulent structures are like comparable to the size of kinetic scales of thermal particles. But if we have structures that are basically larger than the shock thickness, they might corrugate the shock front and introduce some vorticity. So this is what it would require simulating, like doing larger simulations.
I see. Because I'm just trying to understand what's the point of adding the, say, non-resonant instability turbulence if the shock will create particles that will create this turbulence anyhow. So you're going to be adding superficial turbulence on top of self-generated turbulence. And unless the scales are extremely different, I don't know why do this.
So I think so. The idea is that it's not that easy to develop proton-driven turbulence in peak simulations because of how much time does it take and scales. So if you consider like realistic scale separation between cosmic rays that drive this turbulence and thermal electrons and thermal ions, so I think this is the idea. It's not possible to run this in fully self-consistent simulations. That's why we need to somehow do this trick.
I had kind of a very similar question to what you asked, and it was about the corrugation scales. How much larger do you actually have to go to get, some kind of corrugation unstable mode in your simulations?
Yeah, so maybe I can. Okay, I don't have. Maybe here. So I think we would need to. So shock. Kinetic shock transition region is a few ion Larmor radii. So I think basically something larger than this. Because what we see with these fluctuations, they improve particle scattering and modify particle dynamics in the upstream, but they are not transmitted through the shock. So yeah, I would expect that if you have something larger than the shock thickness, so which means larger than a couple ion Larmor radii, then the shock front might get corrugated.
All right, thanks a lot. Are there questions? Any more questions? All right, thank you very much. So I'd like to thank both Karol and everybody else who presented in this session. So thank you for all speakers.